Two.
So you guys excited for that DRA presentation today?
Yeah, definitely. It's going to be interesting.
Pretty good, yeah.
Hello team. Today we're gonna have Mr. Barron coming in to present his project. So I hope he gives us a reason to buy it.
Hello, gentlemen.
Hello, Mr. Sam. How are you?
Right. Welcome, gentlemen. Thank you for coming. Today I'm going to introduce a new product that my company has been working on. It's called the Dielectric Resonator Antenna. I've emailed you all my slides, and I'm hoping that after this presentation I can convince you all to buy one of these antennas. Today I'll show you the implementation of our structure on OpenEMS. Before that, my colleague will demonstrate our prototype that we've built to give you an idea of what to expect.
Hello everybody.
Hello, Ali.
Good to see you, Sam.
Good to see you.
See everybody here. I'm here to present to you the cylindrical DRA prototype. The first thing I have to say is about its scale. The scale is a little too big, but we need to see all prospects of the design. So, although our height is too high on our prototype, it should be a little lower. Our diameter is very close. The way we made this was we used a carpet sheet for a ground plate, a cylinder, a pencil case for a cylinder, and for the coaxial cable we used a piece of string.
So now that you've seen the prototype and you have a basic idea of how the structure looks, I'm going to run you through our implementation in OpenEMS. So I'd like to direct your attention to the screen. Since we chose a dielectric resonator antenna to simulate an OpenEM, we used the conical horn tutorial file as our template. The template seemed the most similar to the DRA at the time. We hoped that our template would need some simple changes and would be a suitable basis for our DRA. The necessary changes ended up being slightly more complex than anticipated, but the file acted as a valid template. This was especially true in the case of the code for a far-field graph. As shown, the structure of a dielectric resonator antenna consists of a coaxial signal that feeds into the bottom of a cylindrical dielectric material that is mounted on a metal ground plane. As you can probably imagine, the resulting simulation will consist of 3 CAD geometries and 1 coax excitation. In the code, as per the template conventions, we initiated all of our important physical constants and variables. These parameters included the maximum number of time steps for the field simulation, as well as the necessary size dimensions, frequencies, and permittivities. Next, we initiate the FD-TD parameters, which runs for the maximum number of time steps with an N criteria of -40 decibels. We set all boundaries to 8-cell perfectly matched layers to absorb this signal at the boundaries. We then begin the actual modeling of the antenna using a few simple geometric methods. First, we define the mesh to house our simulation, which should be large enough to enclose the structure and the relevant measured wave. Then we add the coax cable as well as the signal in the same method, add coaxial port. The ground plane is then added, which is to be a perfect electric conductor, and is then followed by the dielectric block itself. This block is a simple cylinder with a dielectric property added via the set material property command. Now that the simulation is ready to run, we can add dump boxes, which are just a simple way to measure the behavior of the field within the box. The remainder of the code is relatively standard and common across many of the viewed samples. The remaining tasks to run are the near field to far field calculation, and then to write and run OpenEMS, as well as plot the created CAD geometry. Finally, the necessary parameters are listed for the desired plots, and the plotting methods are called. Many of these methods were unchanged from the sample files, as their function is general. A large portion of the physical constants used were taken directly from an example dielectric resonator antenna paper, which is shown in works cited. For the frequencies that we were able to obtain an output for, which is in the range of 5 to 6 GHz, our reflection coefficient graph mirrors the simulation graph in the paper quite well. Outside of this region, the dead zones in our graph could be explained by the possibility of our step size being too large, or that our coaxial excitation was proportionally too large. Unfortunately, neither of these possible errors could be rectified, because any size tweaks in our code at this point made for a code that ran for way too long to be useful. Moving on to the far field graphs. A two-dimensional far field graph mirrors the symmetry of those in the paper. However, it's clear that it's not quite as smooth or as round as it should be. This could most probably be attributed to the proportional size of the coax excitation. However, as mentioned, decreasing the size of this excitation results in faulty running code. The far field graph of our antenna looks much better in 3 dimensions. We can see that it almost encompasses the hemispherical shape that we're expecting. We have no 3D field in the paper to compare our 3D far field with. However, we know that dielectric resonator antennas are expected to emit a hemispherical rounded field. Alright, so now that you guys have a decent understanding of the code that went into the implementation of the dielectric resonator antenna, I'd like to ask if there's any questions people have on the code that you've just seen.
What else did you use besides the conical horn MATLAB code?
Yes, actually, there were 2 main files we had to pull from besides the conical horn. The first of which was the coax cable, which is a pretty invariable thing. So the code that we used was essentially the exact same code that we found online, but it produced the proper waveform, so we just left it as is. That code is referenced in our works site in our report, obviously. And the other one was the model of a human skull, which we used for the implementation of a proper dielectric, as it was the only code we could find that had the dielectric properties implemented properly. So those 2 were the 2 main that we pulled from, other than the conical horn.
What sources of error did you run into while designing the code?
Yeah, actually, errors were the basis for our entire learning process on this design. As I mentioned earlier, we first designed a really simplistic DRA that was just 2 cylinders, the dielectric block and the coaxial feed. Obviously this didn't work because we were missing the coaxial waveguide. We were just using a normal circular waveguide, and the dielectric block was missing all of its main properties too. So obviously this didn't work. And then our other main problem was mesh resolution and step size, which caused the runtime to be excessively large. So we've gotten that down to 3 hours by reducing the step size and the resolution, but it's still excessively long to run.
Did you verify your simulation from any of the previous papers on cylindrical DRAs?
Upon first completion of our simulation, the final product was close to but not exactly accurate. To rectify our design discrepancies, we took our specifications from a paper titled Characteristics of Cylindrical Dielectric Resonator Antennas by Gupta, Rout, and Sivaji, which was published on December 2009. This work is also cited in our report.
So I was wondering, could you implement a hemispherical or rectangular DRA using the similar approach to the cylindrical?
Yeah, quite easily actually. The calculations would be the most difficult part in switching the shape of the dielectric resonator, but the coding would be as simple as changing the shape of the CAD methods in a few lines of code. That would be it. Okay, so if there's no more questions, I'd like to thank you all for your attention and for the ability to present to you today.
Hello, Mr. Sam.
Hi.
I would like to officially accept your offer on behalf of my company.
All right.
Thank you for the presentation.
Thank you, Preet.
Thank you.
Pleasure doing business.
Thank you.
You ready? Let's go!